Good morning to everyone. Welcome to week 10, water treatment with Mike Firlotte. And we will have after the break, we want to take a screenshot for one of our producers. That's the Operators Without Borders Secretariat would like us to do that. So I'd like everybody, after the break, you're all going to put on your videos so we can get that shot. Thank you very much. So over to you, Mike. Session 10, water treatment.
Perfect. Well, good morning, everybody. Yeah, we made it to week 10, 2 more weeks to go. So this will be support systems today. So we'll do a bit of a lecture on support systems. And that's really just some of the supporting roles like electricity, pumps, motors, drives, a little bit about flow. And we touched a bit about pumps, but we'll go a little bit farther into pumps here today. So it is week 10. So my plan is next week, week 11, to have our final big push for content, which will be the little bit of safety and a little bit of water quality. And then for week 12, we'll do a really big review in the form of a test, and we'll use the chat function a fair bit to help us along there. I'm just setting up the presentation here. Hopefully you guys can see week 10 presentation. I'm just putting the chat function up here. There we go. So hopefully you guys are learning lots so far. It is 5 o'clock in the morning for me, so I'm just waking up, and it's a nice warm -2, which is pretty warm for this time of year. So I'm pretty happy. You guys are probably in the 20s, but I'm pretty happy with -2 this morning. Okay, like I said, here's our big thing today. It's going to be electricity, pumps, motors, drives. These are all the things that make things work. So this is kind of a hodgepodge of different topics we'll be covering today. Some of them are a little bit of a review, but some of them are going to be some new content. It's really important content too when it comes to doing the exam. Only because, you know, these are some things that are overlooked sometimes. It's really easy to talk about the water treatment because it's really easy. So we have to also talk about the supporting roles that some of these topics will give you as well. So you guys as operators, there's a bunch of duties that you guys have to do. You just don't come to work, look at a computer screen and things work. You also have to do some checks out there. So you're going to do operational checks, right? You're going to have a check sheet perhaps, and some people have computer tablets that they can use, but regardless, you have to go to the rooms. You have to check what's going on in each of the rooms, look at your pumps, your pipes, your valves. You're going to look for things that are weird, leaky pipes. You're going to hear for different sounds, right? As an operator, you get used to the same sounds in every room. And if things are changing sound, or even having a different temperature, something might be going sideways, and you need to be aware of that. The other big thing is troubleshooting. Once you find that something is a problem, how do you troubleshoot it? How do you go about figuring out what you need to do? And then if there is a problem, who do you report that to? You know, some of the smaller plants, the operator is the mechanic as well. In some of the big plants, there's millwrights and mechanics that work to repair these issues, especially you know, when it comes to electrical stuff. And those are some of the things we got to be careful of as an operator. There's things that you can do and things that you shouldn't touch. And electrical appliances and that kind of stuff, unless you're a trained professional, you shouldn't touch that. You should determine the corrective action, and there should be some procedures there when there is something. If there is a problem with your plant and it will affect the water quality, then your health authority also needs to understand that or know that. But your big thing is you have to check these things. And what I really fear, and I've seen this in the last 10 years, is an operator used to go out and take a look at stuff and have a really good idea what's happening in their plant, where some of the newer operators tend to use the computer. And I was taught really early, when you look at your computer and you rely on the numbers on your computer, what happens if those numbers are false or the instrumentation is false? And it makes, don't rely necessarily on technology. You also need to go out there and physically look and understand what's happening in your plant. Maintenance and operations. So, operation schedule and maintenance schedule are really important. We do that. If you look behind me right here, that's my maintenance schedule. I have a maintenance schedule for both mechanical and over here electrical. And I do that just to make sure that things get done. There's a lot of equipment in my plant, and I want to make sure that everything's scheduled. And so I'm maintaining the best of my ability, the equipment. Because really, when we're producing a lot of water for your product or for your customer, you want to make sure that all the maintenance is done, because downtime could be a really big problem. You have to make sure, what, it happens, you're going to be down time to time. A pump could go, have an issue with a pump or a pipe leaking or something goes wrong, and that you can't prevent that. But I'm always a firm believer is making sure that pumps are serviced, old pipes are replaced, so that you can kind of make sure or limit the amount of downtime as possible. Again, under ideal conditions, you are always here to produce safe potable water, and water for not just your customer for consuming, but also for fire protection. And that means adequate volume and pressure, right? And that the whole system, plant and system, works with no mechanical problems. Again, making sure things operate. We talk a little bit about that when we have to do flushing programs and valve exercising programs. We got to make sure that, because some of these equipment aren't always used, when they are called into action, that they're able to be run. It's like, say, an automobile. And if you just sit and park it and don't touch it for years and years and years, chances are that particular piece of equipment isn't going to start when you need it. So you have to make sure that you're always making sure that the pumps or the motors or whatever you're using is exercised or started or tried every once in a while. And it really should be part of your task. You troubleshoot things. I was always taught early days that everything happens for a reason. And in water quality, definitely that's the truth. Things do change, but there's always a reason for change. So if you always think about that, it might be a very logical reason why it changed, but if you see a change in a sound, a temperature, even a water quality result, there's a reason for it, and you should actually take that very seriously. There could be a water quality problem. It could be a pump problem, right? Things happen for a reason. If I'm using more chlorine for a reason and nothing else has changed, you should be really aware of that. Maybe it's because there was a rain event and more organics came in. Maybe the strength, you change product, and the change of product is maybe you got a product with less strength. Those are the things you need to be aware of. And again, it comes down to record keeping, right? Like, make sure your book is up to date. So if there's more than one operator, you can go, oh, I wonder why the chlorine changed. And you go back in your log and say, oh, right, they put another chlorine, liquid chlorine container online. Hey, that might be a different strength. Or maybe the valve isn't open all the way. These are things that are going to really help you when you troubleshoot issues. Documentation, I can't stress enough how important that is. Again, all troubleshooting uses these steps. What is the symptoms? Find the cause and figure out how do you fix it. And those are really what you do as an operator, right? Operators just don't sit in front of the computer. They have to get in there and understand. Even if they are in front of the computer, look at your trends. Look at things that are changing. Make sure that our instrumentation's correct. And these are things that are really important. And we're going to talk a little bit about instrumentation as we go along here. First thing we're going to do today is we're going to talk a little bit about electricity. And again, we are not electricians, so this is going to be very basic, but it does show up on the test a lot of the time. So let's talk a little bit about electrical energy. And electricity in general can be described as a form of energy, right, caused by the movement of electrons, right, charged particles, electrons. And you got to think of this like flow in your water system. It acts almost the same way. So you have to get your head around that, and we will as we go. The movement of electrons, in this case, for us, movement of water, is called electrical current flow. An electrical circuit can be defined as a closed conducting path through which electric current travels, just like a water system, right? You got a pump in the form of voltage, you have flow in the form of current, and it flows in a conduit, just like our water flows in a pipe. So you have to think of it that way. Source of supply is hey, this is where it originates, right? It's where the component gets the electrical energy, right? Now, all over the world, there's different types of energy and different forms of source of supply, right? We use a lot of hydropower, which means a lot is generated from hydroelectric dams for water, right? Waterfalls and stuff. A majority of our power in this part of Canada, anyway, comes from dams and water flowing over a dam, creating electrical source of supply. We take that power and usually it's going to go to some power generation stations. Some places around the world, they'll use coal, they'll use gases, they'll use different types, and even some of the new energy, solar and wind, these are the things that are used as source of supply. Some of the northern communities in Canada, sadly, they don't have good source of power. So power becomes a real problem because the quality of the power or the source of supply is poor. They end up not getting enough voltage or over voltage, and it really is hard on their equipment. We'll talk about that in a little bit here. So the source of supply could be described as the component of the electrical energy where the circuit originates. It basically produces the electrical pressure that propels the electrons through the circuit. And that's like the pumps that you guys have that propels the water through the pipe. Typical in-house stuff, you'll see something like this. Back in the day, and this probably ages some people, we used to have glass fuses in a fuse panel, right? And that would, if something was, you're putting too many plugs in or using too much current or too much power, it would actually blow the fuse or break the fuse. And you'd have to unscrew it out and put a new one in. And there's very few installations that have that. Some older convection ovens still maintain that. But now they've moved to more a breaker system. And inside, and there's a good picture of this breaker here. Inside that breaker, there's a heated element. So when it gets hot, it will actually separate the circuit, protecting the wires. This is designed to separate the current before damage due to heat or fire happens in your wiring. And it's called a circuit breaker. In your water treatment plants, you're going to have larger voltages a lot of the times. The bigger pumps that you guys use might have bigger voltage than you would have in your own house. Typical house voltage here is 120, 115, 120. In some of our bigger appliances could be 220. But sometimes our voltages in our plants are much bigger. And so you'll have 500 or 600 volt pumps, maybe even more. One of my installations in my pump stations, I had a 4160 voltage. And that's a huge voltage. Those are really big pumps. that device there is a fuse, right? So sometimes in three-phase power, you'll have a big fuse similar to this in those panels that supply those 600-volt plus installations. Again, just a note, these should never be touched by you guys as operators. It should only be done through a trained professional, because these could really do a lot of damage. Talk a little about insulation. So insulation is basically protects the wire. That flow of electrons running through the conductor, you know, you want to make sure that it doesn't touch anything else. So it's coated with usually a plastic or some sort of coating on it, and it prevents it from short circuiting or you being able to handle it without having any damage to yourself. And that is basically insulation. If I have a bunch of different wires inside and they're grouped together and they're inside a larger casing, and this is called a cable. And we see that a lot of times in our bigger plants, a bunch of wires inside a cable. And there's a picture of it here. You can see the wires being protected. Here you got the black insulation, and then it's covered again by another protection layer. And this is basically your conduit or your cable. And it could be used to supply voltage and maybe some other instrumentation means as we go along here. Let's talk a little bit about the load. And when they say electrical load, and that's anything we have out there that uses power, right? It uses the electricity that we plugged in. It's the device that uses the electrical energy. And again, for you guys in treatment, water treatment, a lot of it's going to be lights and pumps and stuff. And sometimes if we have motorized valves that use electricity, this is what it is. Those are our big loads. I would say pumps are going to be our biggest user of electrical energy in your water system. It's important too, though, to make sure that you have the correct voltage and amperage in order to make your pumps operate. Real simple illustration here. You've got a battery as your source supply. You have a protection device and a fuse there, and you can see a control device and a switch, and your load in this case is a nice little light, right? So if there was too much current in the circuit breaker or fuse would blow, protecting the red wiring. In this case, you have a control device and a switch on the other side there, and that can turn on and off the load. Switching is really important too. Typically, as simple as a light switch is a manual switch. You turn your lights on, and basically it completes the circuit and allows it to go. And some of our bigger installations in our computer driven world here, it might go through something called a PLC, and that's a programmable logic controller. And we'll talk a lot about that here coming up because it is a really important topic. Here's your picture of your typical light switch that will turn on your power, right? You turn down that switch, bang, the lights come on, and away you go. Now, in the water treatment world, a lot of the times they'll use something called a PLC. And this is a good example here in the picture of a PLC. Basically, it is taking in all the information from all the stuff in our plant, whether that's valves and instrumentation for level, pressure, and all the stuff, and it's going to a brain, a programmed brain. And that's something that you guys as operators, some operators can do it, but usually it's done through an instrumentation person or a tech person. And what they'll do is they'll say, hey, when this tank gets full, turn the pump off. Or when this tank gets empty, open the valve, and turn the pump on. And all those signals come back in here, and it has to fulfill certain things before it can move on to the next step. And we'll talk a little bit more about the actual circuits of this in a few minutes. Voltage, let's start here. And voltage can be thought of as electrical pressure. So when you guys are doing the test, they're going to ask you what electrical pressure is, and it's voltage. Think of voltage like the pump, right? It's providing the pressure or the how much movement that needs to happen. It forces the current through the circuit. The required voltage is displayed on your loads, right? And so your pump or whatever it is, it's going to say, hey, I require a 600 volt voltage. It's really important. If you don't put the proper voltage to the pump, then you can definitely damage equipment. So it's really important that that's done. You can see here in this two examples, I have a 6-volt battery and I have a 9-volt battery. The 6-volt battery on the left here, it's moving really slow. And it's not very strong, right? You can see it will light it up, but it doesn't light it up as big as, say, 9 volts. 9 volts provide a stronger, it's like a bigger motor in a car, or everything just is bigger. There's more power to push that. So if I had a small pump in my water system and I put a bigger pump in, it's going to be very much more strong of a flow. And that's the difference in voltage. Then we'll talk about current. And current to me is one of the biggest things for you guys as operators, especially if you have pumps and stuff, because what I find that it will tell you the most about what's going on in your pumps. It's the rate of flow in your circuit. It's the water flow. It's measuring flow, right? Only in this case, it's measuring flow of electrons. Amperage is what it's measured in. And this rating is huge for us. When you first put a pump in, you're going to look at the amperage. And if there was a problem with that pump, you guys as operators, it's hard to see what's happening inside that pump. That amperage is going to tell you exactly what's happening in that pump. Because if the amperage gets lower, typically it's meaning the pump is there's less work happening with the pump. And that's a good indication perhaps that the impeller in the pump is worn out. And that's a really good one. When I look and see my amperage starts to drop a bit, that usually tells me that inside that pump, something's worn out. Something's not restricting the flow as much, which means there's got to be either a problem with the check valve or a problem with the impeller. On the opposite side, if I start seeing amperages rise up, that usually tells me a couple of things. I might have a partial blockage in the pump, or my bearings in my pump are starting to wear and causing more friction. And that's the big thing. When amperage changes, you should be very aware of an amperage change of your pump. That's one of probably the most important things as an operator. Look at the amperage of your pump, write it down every day. When that starts to change, you should be very aware of that, because that shouldn't change a whole lot. Again, there's your battery, and it's the flow of electrons moving towards that light or the load that we're talking about today. There's two different types of currents out there. There's two basic forms of energy, and one's how the current moves through the circuit. One's called alternating current, and one's called direct current. And I see them both in the water treatment industry. We'll talk a little bit about the differences between the two. So alternating current, again, you can think of this stuff as current or stuff that's plugged into the wall, okay? It changes in magnitude and direction continuously. So it's always going in a circuit. It's the most common form of electrical energy. And that's the stuff you plug in AC power, right? If you plug it into your wall. Most of the stuff we use is going to be alternating current. On the DC side, again, it doesn't go in this nice wave. It's going to go more flat. It's single one direction. And you can think of this as mostly battery operated equipment. And a lot of times that our battery equipment is plugged in. And so they're going to need something to convert it. They need a rectifier, and a rectifier will actually convert, allow you to plug into AC power and charge batteries. And for those of you who have cell phones and stuff, if you see the picture, that little block that you plug into the wall, that converts your AC power to DC and allows you to charge your laptop or your cell phone. And even when you get a laptop, you see that, the thing that you plug into the wall, it comes with that little black box on the cord. That's exactly that. It's converting AC power to DC to charge your batteries. So really be aware of what your device has. Is it DC power or AC power? And again, DC power usually uses a battery, where AC is direct plug into the wall. Super important. Just like in our water system, there's going to be losses or resistance. And resistance is the property in an electrical circuit now that opposes the current flow. Electrical friction, just like on the water side, there was friction. This is electrical friction. And we call this unit of measure called of ohms. And you can see here, as voltage is pushing the current through the circuit, that hand goes up. That's the resistance. It's resisting. And think of it as electrical friction. All right, let's talk a little bit about power. So power can be described as the rate of work being done or the rate of energy transfer. In electrical equipment, as we know, is usually rated in the amount of power output. Typical, like electrical heaters and lights, can produce 3,000 watts of thermal energy. So that's a 3,000 watt light. Typically, we don't use the watts for some reason. We tend to go with horsepower, right? And I'll just go to the next slide here because it kind of gives you a quick conversion on that. So 1 horsepower is 746 watts. So typically we talk about horsepower. I have a 10 horsepower pump. I have a 400 horsepower pump, and we tend to use that. And that is just the power that this motor can output. We don't say it's 5,000 watts mechanical energy. We'll say it's 10 horsepower. So just think about that. It's just the amount of work that can be done. It's funny, in the heating world and the light world, watts are used a fair bit, whereas horsepower is used more in motors. Do you guys use horsepower a fair bit with your motors? Is that a unit of measure you guys use a fair bit? And what size of motors do you guys tend to have at your facilities? Like, give me an idea. I mean, for us here, I have, to bring water to this plant, I have 400 horsepower pumps to bring water here. And that's a lot of horsepower if you add that all up. So it's usually, for me, that's a fair bit of, that's almost 1,600 horsepower to get water out to my water treatment plant here. Okay, we'll switch gears into a little bit of instrumentation. And we talked a little bit about electrical, right? And, you know, we know that pumps can turn on and valves can be actuated and stuff. And now let's go back, you know, let's rewind. We know that we can turn it on with a switch, right? But it's a lot easier if things are more automated. It's easier for you guys as an operator. You know, every time you want to fill a tank, you guys as an operator would have to look at that tank and figure out when it looks kind of full or kind of empty, and then physically turn a pump on to fill it till you're feeling that it's full. And we'd like to automate that a little bit. And so that if that tank does empty, that you guys can turn it on, or a program can turn it on and sense when that tank is empty and turn it off when that tank becomes full. This is where instrumentation comes in. Again, it's measurement and control, automated. Again, we're going to look at different terms here. And the big term here is called a process variable, or PV. And that's basically to describe the variable in the circuit that's controlled. We want to control something, and that could be a number of different things, such as, say, level in the tanks. We want to make sure that we keep those tanks at a certain level, or that if that tank's empty, it will fill right up, or and turn off again when it's full. Pipes and channels, we want flow rates. Maybe sometimes we want to keep a flow rate at a certain level. So we will control our pump to keep the flow rate at a certain level. For those of you who have filters, filter head loss, or maybe it will automatically trigger a backwash event for your filters. Some of the other instrumentation you guys have, or you're looking at parameters in your treated water. It could be pH, for example, chlorine levels automatically. Turbidity is another big one. These are the things that are used to make decisions as an operator. But how does this all work? Here's some pretty typical instrumentation. The one on the left here is going to be pressure, and the one on the right, the yellow one, is going to be level. Now, let's talk a little bit about that. Let me get my drawing pen out here. So it works on something called 4 to 20 milliamps. And this is really important, so you should write this down. 4 to 20 milliamps. It's important, so instruments are dumb. They don't know if they're measuring pressure or level. They have no idea. All they're doing is they're taking a signal. And that's all they're doing. They're getting a signal from the thing that they're measuring. They have no idea what it really means. And all they're doing is they're making a 4 to 20 milliamps. At 4 milliamps, it always means zero. Zero of whatever it's going to be. And at 20 milliamps, it's going to be the maximum of the scale you choose. So if you put that way, 4 milliamp signal means zero, and where 20 milliamp signal is maximum. And that's why they call that the 4 to 20. In this case here, I would have scaled this level transmitter. So if this is level right here, I would say that this would be 0%, which means my tank's empty, and that my max would be 100. Okay. And that's how I would scale this particular device. Now, keep that in mind. If this is 0 to 100, and that's how I scaled it. And it's a 4 to 20 milliamp scale. That's what it's. When I scale this up, if my tank, okay, say in this case here, you can see the numbers, it's 94.6. So it's going to be pretty darn close to putting out something close to 20 milliamps because I'm pretty darn full. And that's how it works. I have to scale this for what it is. But it always uses 4 to 20. It's going to look at a graph inside there. And it's going to be looking at, okay, at this many, if this is 4 milliamps and 20, when I scale this up, it's going to have different. So I know at 50%, if my milliamps are going to be, say, around 10, for example, I know that it's going to be pretty darn close to a little over 50%. And that's how all these pieces of instrumentations work. It's going to take just a signal in that box or that brain inside that piece of instrumentation. It's going to scale it based on a program so that it spits out a number that you understand. Whether that's pressure or flow, and even in your lab, when you're dealing with any, even your chlorine analyzer in your hand there, right? When they put that color measurement in there and it reads it, all it's doing, it's measuring a voltage, a milli, at this color, it's going to send out this millivolt, and that's going to correspond to a chlorine residual that you guys understand when it spits out. So really always keep that in mind. Instrumentation's fairly dumb. It's how you program it and scale it to make it work for you. All different types, like I said. Again, in order to accomplish type of control, instruments are very precise and operate on low signal levels. And again, the common signal here, and this shows up on the test, is the 4 to 20 milliamps that we just talked about. Super important. There's other types that are not as common, but typically this is the industry standard and what's usually used. It's super common. And again, that's all it's doing is sending a signal. So now when we get going here, just before we move to the next bit here on this page. So let me change color. Go. So if I go back to my level transmitter here, and it's measuring the level in the tank. I'll make an L for level. I'm going to make this my PLC. And I'm going to make myself a pump here. I was never an artist, so I apologize. This looks like a really terrible looking pump. Let's make that blue. Water's coming in, water's leaving the pump, going to the tank. Okay, so in this case here, what? I have some water in this tank. It looks like this tank's pretty empty right now. So if this tank's empty, my level transmitter is going to have a zero reading. It's zero, which means, remember, 4 milliamps. Which means there's no water. So what I'm going to do is that signal coming out of my level transmitter or my sensor, it's going to send a signal to my PLC. And that's my brain, that's my computer. Inside the PLC, this is, there's a program inside here. That program's going to say, hey, when this device here is 0, I need to send a signal to the pump. So there's an input side of a PLC and an output side. So it goes through a logic. It says, hey, when this device is 0, I'm supposed to send a signal to start the pump. This pump goes, oh, I got to start. It will start. It will start filling this tank up. And when this tank gets to a certain level, All of a sudden now I'm not reading 4 anymore. I might be reading 15 milliamps now that the tank's getting full. And that's what I've programmed my PLC to say at 15 milliamps now, turn this pump off. And now that will send a signal to that pump. It shuts off, shuts the water off until it can go again. You can really be complex with your PLC. You can say, I want to hold the level in that tank at 15 milliamps. If it changes at all, I want you to compensate, pump more or pump less using, say, a variable frequency drive or some sort of drive that will provide more or less water if you need it. And those are things that are done that are a little bit more complex in your PLC, but they all run on the 4 to 20 milliamp scale. So some of the things we just saw there is an instrumentation circuit, and that's 3 big components. You saw the sensor, right? The level transmitter is what we used in this case. It senses the process variable. It's saying the level in the tank or the pressure or the flow or whatever we're measuring. It says that, hey, I'm providing this signal, the 4 to 20 milliamp signal. It's going to send it to my controller. We called our controller a programmable logic controller, or PLC. It accepts the signal from that transmitter. It says, hey, I'm going to use that signal, and there's some equations that are put in there by your instrumentation folk, logic, and it will send out a signal to the final control element, or in this case, that was that pump. It receives a signal from the PLC and says, okay, I'm supposed to do this, right? And again, it's just sending a milliamp signal, and that's all it's doing. The brain is in the PLC. So it's super important for you guys to make sure that your PLC, is programmed correctly, protected, especially from power outages, and that you have some spares. Right. Here's a pretty good example of an instrumentation circuit. It's pretty small, but it shows here, this is a flow meter. And basically you can see it's sending a signal from that flow meter in that pipe to a controller. And that little controller is sending a signal to a chlorine analyzer that's saying, hey, if there's not enough chlorine, I need to put more chlorine in. And that's all it's doing. It's taking a look at that. As flow increases, then that number of the flow is going to change how much chlorine you got to put in. And that's all done through a programmable logic. That flow sensor, all it's doing is providing flow in the line. And it says, as you know, as that's coming back, your programmable logic controller says, hey, as I'm getting more milliamp signal, I'll put more input or output to maybe my chlorine pump to give it a bit more chlorine, so I match it. Again, this is a pretty typical looking PLC. This is a training one. And my panel, my PLC panel, it's huge. It's probably about 10 foot tall and take up this whole room. And you open up this cabinet and it's got I have probably close to 200 of these devices in there. So all these little computers. And this is what's keeping this particular plant running. It takes in you can see all the wires coming in here at the bottom, the blue. It's taking in all these signals, and inside here, there's a computer program that computes all that. And then some of those blue wires are output wires, right? It's going to go out to your whatever you're controlling. So it's really important to understand these control systems. It's a pretty new PLC, that one. Again, typical circuit, right? You You have a water pump filling a tank, you got sensors high and low, and a valve, right? It's very simple circuits. Okay. So it's 5:48 my time. Ignatius, we're going to take a quick 5-minute break. And then what we'll do is we'll get, once we come back after that 5 minutes, we'll do a quick picture with everybody. And then we keep going into some more electrical stuff. I don't know if Ignatius, did you hear me on that one? He's not there, but we'll take a quick 5-minute break, guys.
Hello. So we had the break, right?
Yeah, I just started a 5-minute break, Ignatius.
Okay, right. Apologies, I had the distraction.